All right, folks, let's continue probability theory today. We're going to talk about the base rules that's the fundamental of the modern probability theories. We discuss a bit about frequent theorist and a Bayesian theorist. This is classified the basically the Bayesian sort of the um, school. And the basic idea of the Bayesian inference here is well, of course, that's what we talk about the probability as the information um, theory. We see it as the likelihood or the uncertainty. So the idea comes there. Um, and we already discussed a bit about conditional probability. So the idea might come a bit easier for you if you have already familiar, if you have been watching my videos and already familiar with the conditional probability. Let's dive into it. So the probability distribution, the Bayesian rule itself is very simple, just a formula computed probability distribution over possible values of an unknown hidden quantity h given some observed data y equal y. All right, so before jump into this hidden state, I want to explain a bit about the background how this hidden state comes. So in statistics or the scientific sort of perspective, the world is all right. Let me put it this way. So the we are basically living the universe that all comes with observation. So the way we find some phenomenon, let's say, okay, so the coin flip case, we flip the coin, one times tail, one time heads. Those are observation, right? Like you find it as the physical occurrence, physical phenomenon, instead of someone dictate you to this is a coin flip that goes like this side or this side, or stuff like that. It is the natural observation where we haven't laid out any set of rules, so to say. Um, so this is why we are sort of getting this observed value, let's say in this case y. And the hidden state is something that you're trying to capture this sort of the set of rules behind all those observed data. You're trying to figure out what's the natural sort of the rules, nature rules in this world. But that's what we're trying to uh, describe it as the hidden quantity h here. All right, let's now take a look. So the probability of the h conditioned by the y equal probability of h times probability of y conditioned by the h divided by the probability of the y. Um, so the probability of the h conditioned by y times probability of y equal probability of h times probability of y conditioned by the h equal probability of h y. So that again the product rules that we saw already, and as we don't quite know about this hidden sort of quantity h, the probability of the h we call is representing what we know about the possible value of h before any data. So in a natural way that we call it the prior distribution. The terms probability y given by h represent the distribution over the possible outcome y. We expect to see if h, this is called observation distribution. When we evaluate this at the joint point corresponding to observation y, we get a function yh, which is called the likelihood. Yeah, so the term likelihood is showing up the first time here. And we can convert this into a normalized distribution divided by the y, which is known as a marginal likelihood. So yeah, so again, that's a marginal distribution function that you take the sum of those values and um, get the result. And the probability give h probability function h given by y is a posterior distribution because it represents a new belief state about possible value of h. So this hidden condition, hidden sort of state is now described conditioned by the observation y. So what it means that this hidden state has now the contribution from the observed values. That's like what I'm saying when you look at a coin flip that you are start observing the result and you sort of getting more information, so to say, to find this hidden state between um, the actual coin flip itself and what makes the coin flip land on either head or tail. So this is why the posteriors are approximate trial times likelihood, because again the likelihood is this conditional probability y given by x that is here, and parallel distribution. The parallel distribution is the probability of the hidden state. So that's exactly what it means. All right, so this idea of calculating the hidden state from the observed value is also called somewhat the inverse problem. The inverse problem is a problem that instead of mapping h to y, that is from the natural phenomenon to the observed values, we're trying to get uh, the idea to find a hidden state from the observed value. So the forward model, the fx equal y, is now sort of inverted in a sense that we are trying to get this function out of this observed state.